In the first lecture last week, we discussed some very general topics related to the theory of neutrino electromagnetic properties. And today's lecture will be devoted to, mostly will be devoted to the laboratory experiments and investigation of neutrino electromagnetic characteristics. And the next lecture in a week, the final lecture of these three lectures on neutrino electromagnetic interactions, will be devoted to new effects in neutrino electromagnetic interactions, in particular neutrinos in magnetic fields and matter will be considered, and we shall discuss very interesting effects and also discuss astrophysical probes of neutrino electromagnetic properties. So, as I have just announced, the second lecture of this series has a title, Electromagnetic Neutrino Properties in Laboratory Experiments and Constraints on neutrino magnetic and electric dipole moments, neutrino electric milli-charge and neutrino-charge radius. So, and just in order to give a kind of introduction, I would like to speak about probably the most important and interesting phenomena that is the manifestation of neutrino non-trivial electromagnetic properties, and in particular neutrino interactions with the external electromagnetic fields. And I would like to recall and just advertise our review papers published together, one with Carlo Giunti and another shorter one some years before this paper. And this paper is Neutrino Electromagnetic Interactions, A Window to New Physics. This is the title, published in Reviews of Modern Physics in 2015. And this is really the most complete study and summary of neutrino electromagnetic properties. And also I would suggest you to look through and probably read an appendix and supplementary material to this paper, where a lot of very interesting technical details are discussed in some tutorial manner. So, now I would like to start with the addition to our today's lecture, and that will be devoted to the most spectacular effect that appears if we accept that neutrino has non-trivial electromagnetic properties. And first I would like to go back to the year 1957, and this is the citation from the famous Bruno Pontecorvo paper published in the Soviet physics journal JET that year. And this is what the starting point of neutrino mixing and oscillation chapter. So, and we can find the following statement of Bruno Pontecorvo in this paper. He just wrote the following: "It was assumed above in this paper," it means that the existence of a conservation law of the neutrino charge, according to which neutrino cannot change into an antineutrino in any approximation. Well, I would like to recall that at that time, in 1957, there was no notion about there was no experimental confirmation about the existence of different types of neutrinos, and we know now there are electron, muon, and tau neutrinos, but the second type of flavor neutrino was discovered in 1962. So in 57, if people spoken about different types of neutrinos, it means that neutrino and antineutrino. So, and Pontecorvo continued, this law has not yet been established, what I have just mentioned. Evidently, it has been merely shown that the neutrino and antineutrino are not identical particles. And then the most important statement, if the two-component neutrino theory should turn out to be incorrect, what does it mean? It means, as we know, that if not two-component theory is applicable, it means that one should use the four-component neutrino theory, and this means that neutrino is a massive particle. And if the conservation law of neutrino charge or types of neutrinos would not apply, then in principle neutrino and antineutrino transitions could take place in vacuum. So that was the first prediction or discovery, theoretical discovery of the effect of neutrino mixing. So, and the summary is the following. So if the mass of neutrino is non-zero, then neutrino of different types, neutrinos and antineutrinos, can mix, and that was the discovery, the prediction of Bruno Pontecorvo. It was made in 1957. In the same year, so 67 years ago, in the next paper, there's a preprint published by Joint Institute for Nuclear Research, only 3 pages, by the way, with the title Inverse Beta Processes and Non-Conservation of Electronic Charge. Pontecorvo wrote that neutrinos in vacuum can transform themselves into antineutrino and vice versa. So it means that he just confirmed his idea that neutrinos can mix between different neutrino states. This means that neutrino and antineutrino are particle mixtures. So, for example, a beam of neutral leptons, it means neutrinos, from a reactor, and we know the reactor is one of the important sources for antineutrinos, which at first consist mainly of antineutrinos, will change its composition and at a certain distance r from the reactor will be composed of neutrino and antineutrino in equal quantities. So this last sentence and this last statement can be considered as the prediction of the effect of oscillations. So it means that the resulting composition of the flux of equal amount of neutrinos and antineutrinos is the result of effect of oscillations. So it means that 67 years ago, Pontecorvo predicted the effect of mixing and the consequence of effect of oscillations. So we can say that these two phenomena, mixing and oscillations, were proposed by Bruno Pontecorvo in the year 1957, 67 years ago. So now I'd like to recall shortly the main steps. Here, the main steps in neutrino oscillations. Here is a misprint, of course, 67 years ago. First, Pontecorvo proposed the mixing and oscillations. Then, in 1962, after the discovery of the second type of neutrino, that is the muon neutrino, the Japanese group of Sakata, Maki, Nakagawa, Sakata, immediately, using the prediction of idea of Bruno Pontecorvo, just apply this discovery that it could be that the neutrino are mixing particles and there is an effect of oscillations. They just consider this idea for two types of neutrinos that are electron and muon neutrinos in vacuum. However, they only just stated that neutrinos can be considered as mixed states, and they do not go further, and they didn't discuss the evolution of the type of neutrinos in the process of the neutrino flux propagation from the source to the detector. So, and in 1969, Gribov and Pontokorova derived for the first time the probability of neutrino transition or neutrino oscillations between two different neutrino species, and they solved this problem and derived the famous formula for the probability to observe, let's say, the muon neutrino in the initial flux of neutrinos totally composed of electrons. So about 10 years later, in 1978, American scientist Leon Wolfenstein, trying to apply and trying to consider the real situation of neutrino propagation inside quite dense matter in the sun, he just derived the effect of scattering of neutrinos on particles of matter on the process of mixing and oscillations. Then, again, nearly 10 years later, in 1985, Mikheyev and Smirnov, by the way, they just graduated the Faculty of Physics of the Moscow State University. They considered the effect of matter on neutrino oscillations and have found that for a particular value of matter density, there could be a huge increase of the probability of mixing and oscillations. And this effect was called as the effect of resonance amplification of neutrino flavor oscillations in matter. And it was called the MSW effect. In 1971, now we just come to a particular topic of our lecture, Kirchneris for the first time considered effect of mixing and corresponding oscillations between different neutrino spin states, let's say between electron left and electron right neutrinos. And if these neutrinos has non-trivial magnetic moment, and this is just a consequence of effect of non-zero mass of neutrino, as we know, then these neutrinos interact with the magnetic field, and in the presence of transversal magnetic field in respect to neutrino propagation, there is a mixing and oscillations between left and right neutrinos. And again, this effect can be resonantly increased by the presence of matter, and this phenomenon has been studied, theoretically studied, by Akhmedov and independent papers by Akhmedov and Lim and Marciana in 1988. So, and this is one of the most spectacular manifestation of non-trivial neutrino electromagnetic properties, and this effect will be discussed in our lectures in detail. And also we shall consider the astrophysical application of this phenomena. So this is what Pontokorov has proposed, and for simplicity I just recall how this mixing and oscillations were parameterized by Maki, Nakagawa, Sakata. So considered two neutrino flavor, two mass states case. So each of the flavor state is a superposition of neutrino of mass 1 and neutrino of mass 2. And Japanese colleague just proposed to parameterize this mixing by the only parameter the mixing angle, theta, yeah? So, and they also introduce the mixing matrix that now is termed Pentakurva, Maki, Nakagawa, Sakata mixing matrix. So, and as I have already mentioned, Gribov and Pentakurva in 1969 derived a very short and very transparent expression for the probability of neutrino oscillations. This is P is equal is the probability to observe the muon neutrino in the initial flux of electron neutrino once a neutrino flux travel distance x from the source to the detector. And as we know from our lectures in particular, that this probability is expressed as a multiplication of two signs, sine squared double mixing angle multiplied by sine squared pi travel distance x divided by the length of oscillations that is determined by the energy of neutrinos and also depends on the mass square difference of neutrinos. So as we know, the mixing angle and the mass square difference of neutrinos are the most two parameters that govern the effect of neutrino mixing and oscillations. So, and I have already mentioned, I'm sorry that this is in Russian, but formulas are quite transparent. The probability, once again, is shown here, and in this figure, the behavior of this probability as a function of travel by neutrino distance x is shown, and this is really these oscillations, and there are two parameters that determined this curve. This mass square difference and the amplitude of oscillation is proportional, is determined, is equal really to sine squared double mixing angle of neutrino. So, and in 1985, Mikheyev Smirnov, using the result of Wolfenstein calculation of the effect of neutrino scattering on matter on oscillations, they predicted that for a particular value of density of matter, particular value of this parameter A, that is proportional to the Fermi coupling J and the effective number density, well, and when the condition A equal to delta, delta is proportional to mass square difference divided by double in energy of neutrinos multiplied by the cosine double mixing angle. For particular case, this amplitude of oscillations in matter gets its maximal value. So numerator and denominator becomes equal to each other. It means that this sine squared double effective mixing angle gets its maximal value equal to 1. And this is called the resonance effect, Mikheyev-Smirnov-Wolfenstein effect. So what about neutrino electromagnetic properties? After this introduction, I would like to start discussing neutrino electromagnetic properties. And I have already mentioned that if neutrinos has non-zero mass, then inevitably they have neutrinos have non-trivial, not zero magnetic moment. And then due to this effective Lagrangian that couple together neutrino with different spin states, left and right-handed neutrinos, F is the tensor of electromagnetic field, in particular of the magnetic field, then additional mixing appeared due to non-trivial neutrino electromagnetic properties, and as a result, it is possible also to discuss and consider, and it is realized in nature, that the effect of spin flavor oscillations appear. So, and this is illustration of the fact that indeed these spin and spin flavor oscillations can also be increased by the resonance effect. And it was calculated for the first time by Akhmedov and Lim and Marciano in 1988. So the probability of neutrino spin, or in particular here I just showed the formulas for neutrino spin flavor oscillations in the presence of transversal magnetic field, can be also written as a product of two sines squared. Sine double beta that is determined by the effective magnetic moment of neutrinos multiplied by the strength of magnetic field, and also depends on delta that is given by the mass-weight difference, also depends on the vacuum mixing angle. The second term here, V, is the matter potential, and here the third one, indeed, is not important for our discussion now, but it accounts for the possible variation of the constant magnetic field along the trajectory of neutrinos, so-called the twisting magnetic field. And there is a resonance amplification of neutrino spin flavor oscillations due to effect of matter. It means that this effect appears when delta turns to zero, then the amplitude of oscillation, sin squared beta, gets its maximal value equal to 1. And this effect was, once again, was predicted and discussed, and these formulas were derived for the first time by Akhmedov in two papers by Akhmedov and Lim and Marciano in 1988. So there is a correspondence, really, between the flavor oscillations and spin or spin flavor oscillations. Formulas in blue dedicated to the neutrino flavor oscillations, and in red here to neutrino spin or spin flavor oscillations. They are very similar, and the role of the amplitude of flavor oscillations, sine squared double theta, is played by sine squared beta, and the role of mass-weight difference divided by energy in the case of neutrino flavor mixing oscillations is played by this omega. So it is formally equations and formulas are similar, but the meaning is quite different. So here I just stop this introduction, and I would like to stress once again that neutrino spin and spin flavor oscillations in the presence of magnetic field and other more complicated phenomena related to these are the most interesting and the most exciting consequences, probable existing consequences of the fact that neutrino is a massive particle. And this is a real, very important manifestation of non-trivial neutrino electromagnetic properties and non-trivial neutrino electromagnetic interactions. This is kind of, I just stop here in the introduction part, and now I turn to more detailed discussion on the experimental constraints on the most important neutrino electromagnetic properties. And we start with the neutrino magnetic moment. Really, it is the most easily accepted from both from theoretical and experimental point of view among the neutrino electromagnetic properties. However, I would like to mention here just that the most easiest and the most acceptable for future experimental observation are the neutrino charge radii. So the studies of neutrino electron scattering provide the most sensitive method for experimental investigation of non-trivial neutrino magnetic moment. I would like to recall once again that up to now there are no any experimental confirmation from laboratory experiments, as well as from astrophysical observations in favor of non-trivial neutrino electromagnetic properties. So it means that all experimental data on neutrinos are in agreement with the hypothesis that there are no any neutrino electromagnetic properties. So all electromagnetic characteristics such as dipole moments, magnetic and electric moments, millicharge and charge radio and dipole moment are zero. But we know for sure that if neutrino is a massive particle, but this is confirmed experimentally, then inevitably neutrino has at least non-zero magnetic moment. And also, even in the case of the mass of neutrino is zero, the charge radio of neutrino can be not zero. So it means that we can say that from the present point of notion, state of notion, we are sure that neutrino has non-zero electromagnetic properties. So the cross-section of neutrino on electron is composed of two terms. The first one is the standard model contribution that is proportional to the Fermi coupling squared. So the second term can appear if neutrino magnetic moment is not zero, and this value is proportional to the effective neutrino magnetic moment given by this expression, which accounts for the effect of mixing. But I would like to stress that the most correct and the most right way is to incorporate or to introduce neutrino electromagnetic characteristics for the mass states of neutrinos. But we know that in experiments, the flavor neutrinos are detected. So in order to feel or just observe manifestation of neutrino electromagnetic properties in experiments, we should derive an effective neutrino electromagnetic characteristics for the flavor neutrino states. And in this red frame, just the effective magnetic moment of neutrino squared is given as a function of fundamental magnetic moments mu ij that are introduced for the mass states of neutrinos. So it is often frequently claimed that it is possible also to this cross-section to incorporate the effect of charge radius by simple shifting the vector coupling by adding addition term that is proportional to the charge radius, or indeed the charge radius squared. So, but just today we shall see that this is not the whole story, and this is not completely correct. So, I would like to mention once again that if a neutrino has a non-trivial electric dipole moment or electric and magnetic transition moments, these quantities also will contribute to the magnetic part of the cross-section. And here in blue, there is an expression of the effective magnetic moment squared of neutrino as a function of diagonal and off-diagonal magnetic and electric dipole moments. This slide just illustrates the statement I have already made, that an effective magnetic moment is measured in neutrino electron scattering. And in order to just follow this and to understand why it happens, one have to go through two steps. first consider an electron neutrino in the detector as a superposition of mass states of neutrinos at some distance. These neutrinos travel from the source to the detector. And introduce the magnetic moments for the mass states of neutrinos. And then one have to sum up magnetic moment contribution to neutrino electron scattering amplitude for each mass component. And we get the amplitude will be proportional to this sum, where U is the mixing matrix. And the second step is based on the fact that these amplitudes combined incoherently in the total cross-section, and the total cross-section indeed is proportional to the neutrino effective magnetic moment squared, that is equal to the sum of the sum squared that depends on the effective the fundamental magnetic moments introduced for the mass states of neutrinos, and also this effective magnetic moment, electron flavor magnetic moment, is also dependent on the energy of neutrinos and also on the distance neutrino travel from the source to the detector. So this figure illustrates the behavior of these discussed two contributions to the neutrino electron scattering from the standard model, weak interactions, the first term, and from the second term that is due to neutrino magnetic moment. So the first term is shown here by this black dotted line. This is logarithmic scale. This is nearly the flat dependence on the electron we call energy. That is the only value that is measured in such type of an experiment. And these three colored lines stand for this second contribution to cross-section that depends on the value on effective magnetic moment of neutrino. And these lines indicate these contributions of magnetic moment scattering for the values of magnetic moment 3 multiplied 4 or 5 multiplied by 10 minus 11 measured in Bohr magnetrons. So, and from this plot, it is obvious that the lower the smallest measurable electron we call energy is. This is T, yeah, the energy of measured in the experiment. The smaller values for effective magnetic moment or magnetic moment squared can be probed in scattering experiments. So, and here there is an illustration on the the starting point of the studies of neutrino scattering experiments, and the limits, as I have already mentioned, up to now, nothing can be seen in respect to neutrino non-trivial magnetic moment. So all experiments from the very beginning up to now only provide an upper limit for effective magnetic moment of neutrinos. And this first experiments on scattering of neutrinos on electrons were done on Savannah River, and in 1976. Then there was a series of experiments in Krasnoyarsk and Rovno, and these experiments provide the upper limit for magnetic moment on the level of 2 or 4 10 to minus 10 Bohr magnetrons. There's a Super Kamiokande experiment in 2004 provide a limit 1 order of magnitude stronger, something multiplied by 10, few times stronger, and the subsequent experiments provide more severe bound, upper bound on neutrino magnetic moment. So this is a new experiment with the reactor neutrinos. This is result of 2005. You see this, now the value is 9 10 to minus 11. Then Texona collaboration in Taiwan, this also improved the upper bound to 7 10 to minus 11. The first edition of JAMA experiment, this is the Russian experiment on the joint venture of Joint Institute for Nuclear Research and Institute of Theoretical and Experimental Physics of the Kurchatov National Center. The first edition of this experiment provided the limit something 6 10 to minus 11 Bohr magneton. Baruchine experiment in the investigation of the solar neutrino fluxes also give an upper bound about 5.4 10 to minus 11. So, and now I'd like to turn to the most severe bound that have been obtained on the effective neutrino magnetic moment in the investigation of the solar neutrino fluxes by the JAMA experiment. This is Germanian experiment for measurement of magnetic moment of antineutrino. This experiment running for about more than 10 years and under the control of Joint Institute for Nuclear Research and ITEP at the Kalinin nuclear power plant, and they provide since 2012 the world's best experimental limit from reactor neutrinos on the magnetic moment of neutrino, that is 2.9 10 to minus 11 Bohr magnetons. I would like to say that the next edition of this JAMA experiment is called JAMA 2, and another title of this experiment is New Gen experiment, also running in the Kalinin nuclear power plant. And the main task of this experiment to observe, to search for magnetic moment of neutrino and coherent neutrino scattering on nuclei, coherent experiment, and they would be sensitive to the magnetic moment of neutrino on the value of several 5 or 9 10 to minus 12 Bohr magnetons. So now the data is they are taking data, and it is supposed that probably very soon a new upper bound will be obtained for effective neutrino magnetic moment. So this is the photo of Kalinin nuclear power plant. It's in the town of Udomля in the Tverskoy region of Russia. So I will just show several schemes of the experiment, and probably I will not comment on some very important, indeed, technical details. I would like, this is a photo of the devices, and what I would like to comment on is the sensitivity of this kind of experiment. Well, the sensitivity to the effective magnetic moment is determined by several important values, and here is a number of signal events. B is the background level, M is the mass of the target, and T is the measured time. So, the first edition of JAMA experiment, as I have already announced, provide the upper bound. Again, nothing has been seen, so but only the upper bound can be derived, and this bound is equal to 2.9 10 to minus 11 Bohr magnetons. So here are some technical details, several phases of this first stage of the experiment, and it's shown how the upper bound was decreasing in these experiments. And I would like to now to comment on quite important issue. So just in 2010, just before the Neutrino conference of that year, the taxon experiment, this is very similar in Taiwan, very similar to the experiment JEMMA. They provide, as they claimed, and published, by the way, in Physirev Letters, a paper, they claim that they provide a new and more correct theoretical estimation of contribution of magnetic moment effect to the scattering, claiming that the effect of atomic ionization means the effect that neutrinos are not free particles, electrons on which neutrinos are scattering are not free particles, but that they are bound in atom. And so they calculate the scattering of neutrinos on bound electrons and derived theoretically that indeed, as they claim, the magnetic moment scattering should be increased several, 2 or 3 orders of magnitude in respect to the case when neutrinos are scattered on free electrons. And here they put this new result of theoretical estimation calculations in red in this plot, and this blue one shows the result of neutrino scattering on free electrons, and this red one, following to the Taxona paper, is for the case when neutrinos are scattered on bound electrons. So there's a huge increase of dependent on the magnetic moment of neutrino contribution to the cross-section, and they said that they obtain really much severe bound of neutrino, upper bound of neutrino magnetic moment in respect to what has been published at that time by JEMMA experiment. But in our, and these results were reported and also published in the parallel paper. And however, together with my colleagues, Konstantin Kuzakov from our faculty and Mikhail Voloshin, so in a series of papers, we provide a very detailed calculation of atomic ionization effect. And the conclusion is a little bit destructive to our Taiwan colleagues. We have shown that for particular scheme of experiment that is realized in Udomля and also in by the Taxona collaboration, there is no important effect of atomic ionization. So, and that the free electron approximation is quite enough to derive the contribution of neutrino magnetic moment to the cross-section. So we just confirm that JEMMA people and JEMMA result was correct. So now I would like to show several pictures of a new type of experiment, JEMMA 2. So they just move from one reactor to another on Udomля, on Kalinin nuclear power plant, and also they install the detector on the lifting platform and provide experiments. By the way, they move from one reactor to another, and also the distance slightly changed, and also this distance from the reactor, from the source of neutrinos, is also changing in the experiment. So this increases the sensitivity of this kind of experiment to neutrino magnetic moment. So this is some details I'm skipping technical details. And now I would like to attract your attention to a very important fact that indeed what is measured in the scattering experiments, this is an effective magnetic moment that depends, as I have already mentioned, not only on fundamental magnetic moments introduced by the mass states of neutrinos, but due to mixing also depends on the distance between the source and the detector. And this is the most general expressions for effective magnetic moment squared that is probed in scattering experiments. Yeah? And the result is that observable neutrino magnetic moment is indeed an effective parameter that depends on neutrino flavor composition at the detector. And as a consequence, we can derive the following statement that implications of neutrino magnetic moment limits from different experiments, such as, for example, experiments using the fluxes of antineutrino from the reactors or neutrinos from solar, from the sun, are indeed different. And this was studied in detail. I mean, the effect of mixing and oscillations on neutrino electromagnetic properties was studied in detail in our paper published in Physiograph-D together with Konstantin Kuzakov. And we just derive, we consider the vertex function of electromagnetic vertex function of neutrinos, and also we derive the closed expressions for all from factors and electromagnetic characteristics such as Milli charge of neutrino or anapole moment of neutrino or magnetic and electric dipole moments, accounting for effect of mixing and oscillations. I don't want to comment on these expressions and formulas now, but I would also would like only to make a summary of these calculations. So in particular, it's possible to introduce the so-called generalized neutrino charge in respect of what can be seen in the detector. So, and this charge is shown here, and there are contributions from electric charge and the charge radius. So, one of the results of our studies is indeed the confirmation of the already mentioned statement that depending on the baseline corresponding to different experiments, different combinations of fundamental, in particular magnetic moments, can be constrained. For instance, in the short baseline experiments, such as reactor experiments, so the effect of neutrino flavor change is insignificant. So, and what is rarely measured is this value for effective magnetic moment of neutrinos, that is determined by the fundamental magnetic moments introduced for the mass stage neutrinos, and this kind of sum should be calculated. And this is really the expression for the effective magnetic moment for the short baseline experiment, such a JAMA experiment. Yeah? And if we consider another type of experiments, long baseline experiments, then there is another combination of fundamental magnetic moments introduced in the mass states, for the mass states of neutrinos, that is shown here. This is the sum of this fundamental magnetic moment squared multiplied by the squared elements of the mixing matrix. And this particular value is, for this particular value, the solar neutrino experiments, such as Bourg-Sine experiment, are sensitive. So it means that in two types of experiments, short and long baseline experiments, indeed different combinations of fundamental magnetic moments are examined. Once again, this exactly technical confirmation of the statement that implications of neutrino magnetic moment limits from different experiments are in general different. So, and as one of the examples of possibility to constrain magnetic moment of neutrino with the long baseline experiments, I would like to attract your attention to the Bourg-Sine experiment, which is aimed to, that was running up to recent time in the Gran Sasso National Laboratory in Italy, and the main goal was to detect the solar neutrinos. And in this experiment, the effective magnetic moment was constrained on the value 2.8 10 to minus 11 Bohr magnetons. It's very close, numerically it's very close to the result of GEM experiment that is 2.9. But once again, different combinations of neutrino fundamental magnetic moments are sensitive in these two types of experiments. Here is the list of the most important constraints on effective magnetic moments obtained in different types of experiments. That is the table from our paper in Review of Modern Physics. Well, now I would like to switch to another, seems very exotic electromagnetic characteristics of neutrinos, that is electric charge of neutrino. Indeed, in the Standard Model, it is stated, and it can be proven, that neutrino is an electrically neutral particle. So the charge of neutrino in the Standard Model is exactly equal to 0. And this result is the consequences, or attributed to, two important statements and two internal constraints, the gauge invariance and the demand of anomaly cancellation constraints. So there is a general proof in the Standard Model if we consider the case of massless neutrino, so without the model without room for right-handed neutrinos, the triangle anomalies cancellation constraints put certain relations among particle hypercharges that indeed is enough to fix all hypercharges so that they, and consequently the charge, are quantized. So once the charge is quantized, there is no room for neutrino immediate charge, because we know that the value of charges can be whether 1 or 1/3 or 2/3. Yeah, so it means that the fact that neutrino is a neutral particle is fixed in the Standard Model for the mass 0 neutrinos. And also this fact can be proven and has been proven by the direct calculations within the Standard Model for the case of different gauges and methods. In particular, there is a list of papers, including our paper with Maxim Dvornikov of 2004. We have demonstrated in direct calculations of the corresponding loop diagrams that the electric charge in the standard model for neutrinos are exactly 0. But the fact of strict quantization may disappear in some extensions of the standard model when there is a right-handed neutrinos, and it may happen that there is no hypercharge quantization, and as it happens, it means that there is a room for neutrino charge, and the only limits can be set in this case comes from experimental constraints. And we know that let's say electron charge and the proton charge modulus of electron charge are equal to each other with a very high accuracy, or just that the charge the charge of neutron is 0 to very high accuracy from experiments, or that the hydrogen atom is a neutral body, yeah? So it means that in this case, the only experimental results put a limit on neutrino electric charge, so we can speak without violation of the particular theoretical framework that neutrino can be merely charged particle. So it is not excluded, totally excluded by the present experiments on neutrinos. And so taking this into account, some years ago, about 10 years ago, I just have added the third unobservable. I would like to stress once again that in JAM experiment there is no observation for the contribution of magnetic moment to cross-section. By the way, there is no even observation of the standard model contribution. What is seen only the background and nothing more. So it means that all discussed terms like the standard model contribution or the magnetic moment contribution are within the background, yeah, that is measured, yeah. And I have added the third unobservable effect to this cross-section, and due to possible non-trivial neutrino electric charge. So that is an expression that this term is proportional to the Milli charge of neutrino squared. And just in order to be in agreement with the experimental data, it is possible to get an upper bound for neutrino Milli charge from the data of JAM experiment, and it was derived that it is 1.5 10 to minus 12 Bohr magneton. And with the new edition of the JAM experiment, new JAM experiment, that started in 1992 and now it's running, and I have already mentioned that the sensitivity for effective magnetic moment will be decreased to the level 5 or 9 10 to minus 12 Bohr magnetons, and if there will be no indication for some additional terms in the cross-section, then the upper bound on the neutrino Milli charge will be lower about 1 order of magnitude, about something 1 10 to minus 13. This result, the present result, the present limit from JAMA data is also included by the particle data group, calibration to the table of neutrino properties, in particular neutrino electromagnetic properties, since 2016 up to now. Yeah. So now I would like to switch to another important characteristic of electromagnetic characteristics of neutrinos, the charge radio, that indeed, as I have already mentioned, is the most accessible for experimental investigations among the electromagnetic properties. And also there is a big interest and big question of astrophysical bounds on this value. So charge radius is oftenly claimed is related or inherently related with the anapole moment, and in literature we can oftenly come across the claim that in the standard model the anapole moment is proportional to the charge radius. But as we have discussed with Carlo Giunti in our paper in Review Modern Physics, indeed these two electromagnetic properties are not connected in such a simple way. So the point is that the charge radius and anapole moment are not differently distinguished in the cross-scattering experiments. So they act together. So there is a superposition of the effect, but not as it may follow from the statement that anapole moment is proportional, is equal to 1 divided by 6 charge radius squared. So, just here I would also like to mention a series of papers and theoretical investigations by Jose Bernabé collaborators who just tried to solve the problem of defining the charge radius as a finite, not divergent, and physical value, because if you just make calculations, for theoretical calculations for the charge radius for the case of not zero mass of neutrino, then the result will be not finite and even gauge dependent. So it means that in this case the charge radius can be considered as a physical value. And what Bernabé collaborators has done, they just include additional diagrams that also contribute to the scattering of neutrinos to charged leptons, such box diagrams, and they just introduced the so electroweak charge radius that indeed can be determined as a physical value that is manifestly not dependent on our gauge fixing parameter and finite. So again, I would like to flash to our investigation of neutrino electromagnetic properties, accounting for the effect of mixing, and in particular, one of the results of our studies, we have shown that neutrino charge radius in neutrino electron scattering experiments cannot be considered as just a shift of the vector coupling constant by adding the term that is proportional to the charge radius, but also there are other contributions that comes from the flavor transition charge radius. So that is one of important results of that paper. And then recently, together with our Chinese and Italian colleagues, we have investigated the possibility of manifestation of this not diagonal charge radio of neutrinos, and we implement this possibility in the study, in the analysis that we have performed of the coherent experiment data, and derive for the first time the constraints on the non-diagonal charge radio, and these constraints were highlighted by the editors of Physical Review D and by their suggestion. So at the end of the year, the editors select the most important result published in this journal during the year, and they select our result and as an important result, and indeed we are very proud of this. And starting from 2018, the constraints we have obtained on the non-diagonal charge radius squared using the coherent experimental data are listed in the table of neutrino properties that is published by the particle data group in their reviews on particle properties. So here are the list of constraints on neutrino charge radius, and now we are well equipped and for the further discussion of neutrino electromagnetic properties, and in particular for investigation of possible astrophysical applications of neutrino electromagnetic properties. And at first, of course, we shall discuss the most important neutrino electromagnetic effects, neutrino electromagnetic interactions that exist due to non-trivial neutrino electromagnetic properties, such as effective magnetic moment and effective or fundamental neutrino millicharges. And that will be the subject of our next, the third in this series lecture that is planned to May 13. So thank you for your attention.